It's pretty amazing to think about, isn't it? Like in this whole AI explosion we're in, we're just surrounded by so much data, text, images, you name it. And it kind of makes you wonder, how does AI actually get all this unstructured stuff? How does it even know where to look and how to connect the dots in ways we might not?
Yeah, it's a huge question, right? And it's at the heart of a lot of the really exciting developments in AI. Because it's not just about holding on to tons of data, it's about making sense of it all in a way that AI can actually search through it intelligently and analyze it, even when you don't have exact keywords to go on.
That's it, exactly. And that's the whole point of our deep dive today. We're getting into vector databases. Think of this as like your crash course into why these things are so crucial for how AI works now and how they crack the code of high-dimensional data, which is what all the sources keep calling it. We've got some really interesting stuff here that compares these new databases to the old school ones you're probably used to and shows how they're being used in the real world. So our mission today is pretty simple. Figure out why vector databases are such a big deal for dealing with this complex, high-dimensional information.
And it really is a pretty fundamental shift, like we said. It's not just a minor upgrade, it's a whole new way AI is looking at and handling information.
All right, so let's break down one thing right off the bat. This term high-dimensional data keeps popping up. What does that actually mean for us regular folks, and why can't our good old databases just handle it?
Okay, imagine you take some text or an image, right? And you feed it into a cutting-edge AI model. What that model is trying to do is understand the meaning, the context, the whole picture. So it turns that raw data into a bunch of numbers, a big long list, which they call an embedding or a vector. And each number in that list basically stands for some aspect of what that data means. So the more advanced the AI model, the more subtle details it's picking up, and the longer that list of numbers gets. And that's what they mean by high-dimensional pick. These vectors can have hundreds, sometimes even thousands of these numerical dimensions.
Wow, can you give us an idea of how many dimensions we're actually talking about? It's hard enough picturing hundreds, let alone thousands.
It really is a totally different way of thinking about data. Like, for instance, OpenAI has this model, text embedding ADA002, which is a bit older but still pretty powerful, and it creates vectors with 384 dimensions. But their newest one, text embedding 3 large, that thing jumps to over 3,000 dimensions. 372 to be exact. Even those commonly used models like BERT, they produce vectors with 768 dimensions, and more efficient versions like the StillBERT are still around 512.
So you're telling me we're trying to compare maybe millions of these super long lists of numbers to find ones that are similar in meaning. It's like trying to find a specific grain of sand on a beach, but instead of just location, you're comparing what each grain is made of. That just sounds impossible for a regular database.
You got it. Those traditional relational databases, the ones that arrange everything in neat tables with rows and columns, they're amazing for structured data and precise searches. They're like the kings of finding exact matches. But when you ask them to find things that are similar in meaning in these huge high-dimensional spaces, forget it. They weren't built for that. They don't have this thing called approximate nearest neighbor search, or ANN, built in, which is how you quickly find similar vectors without comparing every single one. And then there's the problem of figuring out how similar two of these massive vectors are using things like cosine similarity or Euclidean distance. Doing that across thousands of dimensions for every single data point, well, it just gets incredibly slow and eats up your computing power.
Okay, so our old reliable databases are hitting their limit with this new AI data, and that's where vector databases swoop in to save the day. Tell me more about these specialized tools.
It's exactly. Vector databases like Pinecone and Milvus, they're designed from the ground up to handle these high-dimensional vectors efficiently. And what's really cool is how they organize all this data. They use these special indexing methods that are made for high-dimensional spaces. Think of stuff like hierarchical navigable small world, HNSW, or inverted file, IVF. These are basically like smart shortcuts through that complex space of meaning, so they can search crazy fast and at scale for those approximate nearest neighbors. No more comparing your query to every single vector in the database.
So it's like they built the super efficient, multi-layered map that lets you zoom right in on the most relevant areas in this abstract world of meaning.
That's a great way to put it. Now, the sources also talk about this thing called Vizai ICE, which stands for Facebook AI Similarity Search. Where does that fit in? Is that another vector database?
That's what I was wondering too.
FAISS is a really powerful open source library, and it's specifically made to speed up similarity searches. It uses many of those clever indexing tricks we talked about. But here's the thing, FAISS by itself isn't a complete database. It's more like a super specialized engine. It needs to work with other systems, like a key value store like Redis, to handle all the basic database stuff, creating, reading, updating, deleting data, what they call CR road operations, and making sure your data is saved permanently.
Got it. So FIS is like a high-performance engine, but not the whole car. Now, the sources also mention managed and self-hosted vector databases. What should someone consider when choosing between those?
Yeah, that's a really important practical choice. Managed services like Pinecone, they take care of a lot of the headaches of running and scaling the database. They handle things like automatically adjusting resources as you need them, and they often come with security features built in, like encryption for your data when it's stored and the ability to set up private network connections, which is often called VPC peering. The trade-off is usually in how you pay. Managed services typically price based on how much you use, like how much data you store or how many queries you make.
So it's like all-inclusive, but you pay for the convenience. Makes sense. What about self-hosted options like Milvus? What are the ups and downs there?
With self-hosted, you've got way more control over your infrastructure, and depending on how big your needs are, it could potentially be cheaper. But with that control comes the responsibility of managing everything yourself, all the DevOps stuff. You're in charge of scaling as your data grows, handling security, basically making sure the whole thing runs smoothly. It's a classic trade-off, convenience versus control.
So it's like renting an apartment where the landlord takes care of everything versus owning a house where you're responsible but have more freedom. Gotcha. Now, the sources also mention LangChain. How does that framework play into all of this?
LangChain is awesome. It really simplifies the whole process of working with vector databases. It's like a middleman that makes it easier to create those embeddings from your data and then talk to different vector databases. It has pre-built integrations and tools that handle some of the trickier parts of working with AI models and different database systems. It basically helps you connect all the pieces to build AI applications that use vector search without having to be an expert in every single part of it.
Okay, so we've got the challenge of high-dimensional data, vector databases as the solution, and tools like FAISS and LangChain to help us along the way. Now let's get into the nitty-gritty. How does this all actually work in practice? The sources give a basic architectural flow.
Right. At the highest level, there are a few key stages. First, you got to take your raw data, which in this example is text, and turn it into those numerical embeddings we talked about. This is usually done using an embedding model, and the example uses OpenAI's API for that.
So step one, transform your data into a meaningful bunch of numbers. Check. What's next?
Next, you got to store those embeddings in a vector database. The example uses Pinecone. And these databases are built to store these high-dimensional vectors and, super importantly, index them in a way that allows for that super efficient similarity searching using those special indexing methods we discussed earlier.
And that's where LangChain comes in to streamline things.
You got it. LangChain makes generating those embeddings and loading them into Pinecone easier, and helps with querying them later on too. It gives you these handy classes and functions that take care of a lot of the behind-the-scenes details. And the sources are spot on about emphasizing security here. Things like managing your API keys securely, ideally using environment variables so you're not putting sensitive info directly in your code.
Security is key, absolutely. The sources also talk about batch generation and storage of embeddings. Why is it better to do things in batches?
Well, when you're working with mountains of data, generating and storing embeddings one by one would take forever and be super inefficient. You'd probably also hit rate limits from those embedding providers, like OpenAI's API, which limit how many requests you can make in a certain amount of time. Batch processing lets you send a bunch of data to the API at once, which speeds things up massively. And the code examples in the sources even show how to build in retry logic to handle those API rate limits automatically, which is a really practical thing to consider when you're building real-world applications.
Yeah, those API limits are a real pain. What about actually searching the database once you've got all those embeddings stored? How does that work?
So for searching, you take your query, whatever you're looking for, and turn that into an embedding too, using the exact same AI model you used for your original data. Then you send that query embedding to your vector database and ask it to find the most similar stored embeddings based on a chosen similarity measure, like cosine similarity. Think of cosine similarity as measuring the angle between two vectors. The smaller the angle, the more semantically similar they are. The sources mention that you might see some cold start delays with a brand new index until it's fully built and optimized for searching. It's like a new library needing time to organize all its books before you can find what you need quickly.
Yeah, that makes sense. Got to organize for efficiency. Sound like LangChain helps with this querying process too.
Exactly. LangChain has simple methods to do these similarity searches in just a few lines of code, like that vector store.similarity search example in the sources. It really hides a lot of the complicated stuff about talking to the database.
Cool, so we've got the basic workflow down. Now let's dive into some of those more technical, architectural, and performance things that the sources highlight. Indexing strategies seem like a big deal.
They are super important for how efficient vector databases are. Like we talked about before, different indexing methods have different trade-offs. HNSW, that hierarchical navigable small world, it's great at finding a high percentage of the really relevant results, what they call high recall, but it can use a lot of memory. Then there's IVF, inverted file, which can be faster for queries but might not be quite as accurate, maybe missing some of the less obvious matches. Which indexing strategy you pick really depends on what your application needs, Speed King, or do you absolutely need to find every relevant result, even if it takes a bit longer?
So it's about finding the right balance for your needs. Makes sense. What about handling truly massive data sets and dealing with a ton of search queries? How do vector databases scale up to that?
That's where things like sharding and horizontal scaling come in. Vector databases often split their data across multiple independent units, called nodes as sharding. Then, as your data grows or you get more searches, you just add more of these nodes to the system that's horizontal scaling. This distributed architecture lets the database stay fast and available, even when you're dealing with like petabytes of data and millions of queries every second.
The sources mentioned dimensionality reduction techniques like PCA2. What's the benefit of making those embeddings smaller?
Dimensionality reduction, like principal component analysis or PCA, can reduce the number of dimensions in your embeddings while trying to keep as much of the important meaning as possible. It's like simplifying a complicated map to show only the main roads. This can make calculations faster during indexing and searching and also save you storage space. But there's a trade-off, of course. You might lose some of the fine details, meaning that the original high-dimensional embeddings had.
So it's a balancing act between efficiency and keeping all the info.
Got it. What about keeping track of how well these systems are actually doing in the real world?
Monitoring is super crucial. The sources talk about tools like Prometheus and Grafana, which are like the industry standard for tracking key performance indicators. For vector databases, things like query latency, how long it takes to get your search results, and recall at K, which measures how often the truly relevant items are in the top K, results are important. These metrics help you see if your system is meeting your goals for performance and accuracy, and let you tweak your indexing and other settings.
And what about keeping the data consistent? The sources mention that different databases might handle updates differently.
Yeah, consistency models determine how and when changes to your data show up in the search results. Pinecone, for example, often uses what's called eventual consistency, meaning there might be a tiny delay between when you add new data and when it's fully searchable. Milvus lets you configure consistency levels, so you can pick a stronger level if your application absolutely needs it, but that might slow things down a bit. So different databases balance speed, accuracy, and how up-to-date the search results are differently. And of course, cost is always a factor.
Absolutely. We mentioned this before, but it's worth repeating. Managed services often have simple usage-based pricing, but those costs can add up as you use them more. Self-hosted options might have lower costs for the infrastructure in the long run, but then you've got the cost of your team's time and effort to manage and maintain the system. It all comes down to what your specific needs and resources are.
Right, gotta weigh those options. And lastly, security. Sounds like vector databases have some built-in security features, but it's still something users need to be mindful of.
For sure. Managed services like Pinecone usually encrypt your data at rest by default, which is super important. Access control, often called role-based access control or RBAC, lets you define who can access and change your data. For really sensitive applications, setting up VPC peering creates a secure, private connection so your traffic doesn't go over the public internet. And no matter what, managing those API keys properly, keeping them secret and not putting them directly in your code is crucial, whether you're using a managed or self-hosted solution.
All right, we've covered a ton about how vector databases work and what to consider. Now let's zoom out a bit. Where are these technologies actually being used in the real world to build cool AI applications? The sources give some interesting examples.
Recommendation engines are a big one. Think about how platforms like Spotify suggest new music or podcasts. They're probably using vector search behind the scenes to find content with similar sounds or that users with similar tastes have liked. Another big one is semantic search, searching based on the meaning of your query instead of just keywords. This is huge for things like digital libraries, knowledge bases, and content management systems, where you need to find information based on concepts, not just specific words. And then there's conversational AI chatbots that can use vector databases to pull relevant information from past conversations or knowledge bases to give more helpful and context-aware responses.
Wow, so those are all examples of AI we use every day. It's wild to think that vector databases are the unsung heroes behind those experiences. The sources also bring up those cold start delays again and suggest pre-computing embeddings as a way to deal with that. Can you explain why that works?
Sure. If you've got a big chunk of existing data, like all the articles in a digital library, you can pre-process it all by creating embeddings for everything and storing them in your vector database before you even launch your application. That way, when people start searching, the database already has tons of pre-computed vectors to compare against, so you don't get that initial slowdown while the index is being built. Then for any new data that comes in, you can create embeddings and add them to the database as you go.
And finally, the sources mention accuracy metrics like recall at K. Why are those particularly important when talking about approximate nearest neighbor search in vector databases?
Well, because ANN search is all about making approximations to get that crazy speed and scalability that vector databases offer. It doesn't guarantee you'll find the absolute perfect nearest neighbors every time. So metrics like recall at 10 tell you how often the really relevant stuff actually shows up in the top K results your database gives you. For example, recall at 10 tells you how often the most relevant things are actually in the top 10 results. This helps you see the balance between search speed and accuracy and fine-tune your settings to find the sweet spot for what you need.
This deep dive has been really eye-opening. So to wrap it up, these vector databases are now essential for searching and making sense of all this complex, high-dimensional data that's behind so much of AI. They've basically solved the problem that regular databases had with this new kind of data by using clever indexing for super fast, approximate nearest neighbor searches.
Exactly. They're driving a ton of the intelligent applications we use every day, from recommendations to smart search.
And as AI models keep getting better and making even more complex, higher dimensional embeddings that capture all these subtle nuances of meaning, it really makes you wonder, how will vector database technology keep up? Will we see even cooler indexing methods? How will they handle the increasing amount and complexity of AI data while still giving us lightning-fast and accurate results? It's a really exciting field to keep an eye on.
It really is. What happens with vector databases is going to shape what AI can do in the future in ways we can only imagine right now.
Well, that brings us to the end of our deep dive today. Thanks for joining us on this journey through the fascinating world of vector databases. We hope you've got a much better grasp on this crucial technology that's powering the AI revolution.